My presentation now. I will talk more in detail about the Belgian situation, and since in Belgium the energy regulations are regional responsibilities, I will specifically talk about regulations in the Flemish region of Belgium related to overheating. So some background about Flemish EPBD regulations. Then I will talk about the methodology that we use for overheating assessment. I will talk about compliance. I will compare the results of the simplified overheating indicator used in regulations with some dynamic simulation results and measurements, and then come to conclusions. In the Flemish region, we have a number of requirements related to the energy performance in buildings regulations. We have requirements at three performances: the thermal insulation requirements, the end use requirements, and the indoor environmental quality requirements. The energy use, we in Belgium both have a requirement for the maximum net energy demand for heating, and also for the maximum level, which is a measure for the total primary energy use of the project, including energy use for space heating and cooling, domestic hot water, and auxiliary energy use, dwellings at least. As the figure shows you, the requirements for the E level have been strengthened over the past 10 years. Preparation of requirements for nearly zero energy buildings by 2020. This also has an effect, of course, on the overheating measures that need to be taken in order to meet all these requirements. In overheating, the Flemish regulations, and this is true in fact for the other regions in Belgium, they have defined an overheating indicator based on a simplified calculation method, for which maximum value should not be exceeded for residential buildings. Overheating requirement does not exist for non-residential buildings. About the methodology then, the background of the calculation method in Belgium, both for assessing use and for assessing overheating, is the semi-steady state calculation method defined in ISO 13790, which is based on a calculation where the whole housing unit is considered as a single zone. In calculating the energy need for space heating, the monthly energy for heating is calculated by the heat losses and minus the utilized gains, the gauge are used to reduce the space heating energy needs. That's a well-known equation, I believe. So to assess which action of the heat gains, both solar heat gains and internal heat gains, are useful to reduce space heating, the gain utilization factor is defined, which depends on the gain-loss ratio, the monthly gain-loss ratio. The result of this calculation is that for each month of the year, the monthly energy need for space heating is calculated, which is represented by the blue line in the graph below. Since all heat gains are useful to reach the spacing energy need, you may have during some months also heat gains which are not utilized. They are in the graph by means of the red line, And these non-useful gains, in fact, contribute, or we can consider them to contribute to an increase of the indoor temperature above the set point temperature for spacing in this case. Now, it's in fact the background of the definition of the overheating indicator. This background is also briefly described in Annex I-4 of the ISO standard, but it relates overheating to the non-utilized heat gains, as the equation shows. These non-utilized heat gains are also defined on a monthly basis and are normalized by dividing the non-utilized heat gains by the loss coefficients and multiplying this ratio by the total time of the month. And so the result is a temperature excess expressed in Kelvin hours. And by summing up all these monthly normalized excess heat gains, we get an overheating indicator for the full year with units Kelvin hours. And so this value should not exceed a given value in the requirements. Okay, is cooling then dealt with? Also, cooling is defined based on the ISO standard, in which the monthly cooling energy need is calculated by considering the heat gains and subtracting the useful heat losses, in which in this case a loss utilization factor is introduced. Now, what is specific for the Flemish regulation is that this monthly energy need for cooling is multiplied by a probability of installing cooling. This is really the fact that it's not very common in dwellings to install a cooling system. But of course, when when occupants will experience overheating problems after occupation, they may still decide to install a cooling system. And to assess this probability of installing cooling, this factor PC is multiplied, is a multiplication factor for the monthly energy need for cooling. You see the equations which are to define this probability of installing cooling. There's a difference between a situation where no cooling system is installed at the moment of occupation. In case the probability of installing cooling will be 0 on the condition that the overheating indicator Y is lower than a given threshold value. And the probability of installing cooling will be 1 when the overheating indicator is larger than the requirement, in fact, for overheating. And in both values, the probability is interpolated between 0 and 1. The cooling system is already installed at occupation. Cooling will be fully operational, and this probability will be equal to 1. So this is the way the methodology works in the Flemish regulations. Let's take an example. The example related to a real case. It's a detached passive house. It's got a wood frame construction. Some measures are taken to reduce the overheating risk by installing external solar blinds at the south and west facade of this house. The calculation results show that the overheating indicator equals 13,000 Kelvin hours per year. This is a value which is lower than the requirement, which is equal to 17,500 Kelvin hours a year. And the associated probability of installing cooling is 50% here. So this example complies with overheating requirements, but in the calculation of the energy performance level, certain energy need for cooling has to be taken into account because the probability is larger than 0. Now, can these values vary? Just for example, we have changed some of the design parameters in this house. First, assuming a poor design where the glazing area is 15% larger than the original case, where there's no solar shading. In that case, the overheating indicator Y will have the value of 41,000 Kelvin hours, which is larger than the requirement. So in this case, the design would no longer be compliant with the requirements, and so the designer needs to change his design. Another example, in case we have an improved design, in this case with heavyweight construction, with a smaller glazing area, and with the external solar blinds with a more advanced control. In this case, the overheating indicator is 7,200 Kelvin hours, which is lower than the lower threshold value of 8,000 Kelvin hours. And so here, the calculation shows that the probability of installing cooling is 0. And so in this case, the design would meet the overheating requirements, and as well, the no cooling energy needs need to be taken into account when the E level is calculated. So in terms of compliance, all energy performance requirements need to be assessed in Belgium at the moment of completion of the works. There is a EPBD assigned to do this job. He creates necessary input in the software and communicates all results to the regional authorities by means of a central database. The authorities check whether the requirements are met. In case this is not the case, the builder is charged with a fine proportional to the size of the error. So also in case the overheating requirements are not met, the builder receives a fine. Since all these information is available at the central database, the authorities can also report on to what extent the requirements are met, and the graph shows a distribution of all submitted reports with corresponding overheating indicators are reported. Each line represents another year of a building permit. You also see the maximum requirement of 17,500 Kelvin hours, and the lower threshold below which the probability of installing cooling is equal to 0. So as you see, only a limited number of reported projects do not meet this overheating requirement. As in more recent projects, you see that the overheating indicator, for instance, in 2013, achieves lower values than 10 years ago in 2006. There are also a number of tools which have been developed to make product data related to summer comfort technologies more available to EPB reporters and to designers. For instance, in Belgium we have an EPB product database, which is a voluntary scheme where manufacturers may include their products provided their product performance properties are checked by a third-party control. And the database also includes properties of sunscreens. For instance, you see an example in the table below with transmittance, solar transmittance and reflectance values for each sunscreen. Information about the relation between the overheating indicator and the results of dynamic simulations. The overheating indicator, it's a simplified method to assess comfort. It's assessed at the level of the whole building, of the whole house, while comfort is in fact rather a problem of a single room and should be addressed at the level of a single room if you want a detailed comfort assessment. And for this purpose, dynamic simulations, where a time series of hourly temperatures is evaluated, is a more appropriate approach for a detailed assessment. So in the following slides, I will use a assessment method based on dynamic simulations to compare the comfort to the overheating indicator. We'll use temperature exceedings above a given PMV, typically a PMV predicted mean vote of 0.5, which corresponds for residential situations to upper temperature of 26 degrees C. And the temperature exceedings above this temperature are counted. We can also include weighting factor, for instance, based on the predicted percentage of dissatisfied, the larger amount of dissatisfied compared to the situation at 26 degrees C. And in this case, we can count the number of weighted temperature exceedings per year. As a requirement, the European 15251 gives as a guideline that the temperature exceedings should not be larger than 3% per year during occupancy. Okay, let's have a look at some results. First, we consider the calculated temperature exceedings based on dynamic simulations and the overheating indicator calculated for a reference building, an imaginary reference building, a single floor, single zone. You see the facade at the top, and in calculations, both dynamic as with the overheating indicator, the whole reference is considered as a single zone. You see here the relationship between the overheating indicator and the temperature exceeding hours, with the level of 3% of time in the full year, temperature exceedings above 26 degrees, and also the level of 10%. Now you see that the lower threshold value of the overheating indicator in this example corresponds more or less with the target value of 3%. As at an overheating indicator with values larger than this lower threshold value, you see that the exceeding hours may become larger than 3%, even larger than 10%. This value more or less coincides with the requirements proposed in the EPB regulations of this case. So you see, in fact, having or fulfilling the overheating requirement of 17,500 Kelvin hours doesn't necessarily guarantee that all overheating problems are included in the design. So it's rather a method which will prevent the most severe overheating problems, but will not necessarily guarantee a very good summer comfort in all situations. So for the use of this probability of installing a cooling system after occupation is certainly meaningful to address these situations. In another example, the result of dynamic simulations for multi-zone dynamic simulations have been compared to the value of the overheating indicator for 3 different housing typologies: a terraced house, an apartment, a detached house, with 3 different performance qualities. And in multi-zone calculations, the dynamic calculations, each house is considered to consist of 2 zones. For we see the results of the dynamic simulations. So the blue dots give the results for one zone, the red dots give the results for another zone. And as you may expect, the overheating indicator prevent overheating in one of the zones in one of the zones in the building. So they have an overheating indicator which is lower than the requirement. In most of the simulations this is the case, but you may still have some zones in the house which have which, based on the dynamic simulations, show to have exceeding hours which are much larger than 10% a year, and so which may experience still severe overheating problems. So again, meeting the requirements of the overheating indicator does not necessarily mean that summer comfort is achieved in all rooms of the house. You also see when you consider different typologies that there's a larger deviation between the results of the overheating indicator and the dynamic simulation. The correlation becomes weaker between both values. I also show a comparison between the results of the overheating indicator and measured indoor summer temperatures, in this case 5 passive houses. In all cases they met the EPB overheating requirements. They had to be able to be built in Belgium. In this the measured interior temperatures, daily mean interior temperatures, measured during the months of August and September of this year for all these houses, are compared to the daily mean exterior temperatures. And what we see is that when you consider the summer situation, there's no clear relationship between the measured values and the results of the overheating indicator. For instance, the purple dots, this case, show to have the largest overheating indicator. The green dots show to have the lowest overheating indicator of these 5 passive houses, but the temperatures in summer, daily temperatures, this difference in overheating indicator is not reflected in the measured values. In fact, we see in measurements that in the achieved temperature, the occupant plays an important role. The way how he interacts with the building, when he opens windows, when he lowers sunscreens, etc. This is an important influence on the indoor temperature, and of course this is not taken into account except in a standardized way in the calculation of the overheating indicator. Okay, conclusions. In Belgium we use the overheat indicator based on a simplified calculation method. We know correct comfort assessment is only possible by means of dynamic simulations at room level. But the overheating indicator, which assesses the level, assesses summer comfort at the level of the housing unit, still allows the designers to take measures to prevent severe overheating risk. As the results of dynamic simulation showed, and the comparison with the results of the overheating indicator, to meet the overheating requirement does not end overheating problems in all rooms. So for this reason, the use of this probability of installing active cooling, and in fact predicting a fictive cooling energy use, is necessary. In fact, we've seen with experience over the last 10 years that the EPB approach has increased awareness of sustainable summer comfort measures, both in building industry and in design. I thank you for your attention.